Welcome back, calculus fans. This is going to be a lesson about inverse trig functions. Really, it's a lesson about the derivatives of inverse trig functions, because that's what this is all about, right? Derivatives. So by now, you should already know what inverse trig functions are. So I'm not really going to talk much about what they are in this video. You know, that's kind of a prerequisite for this course is having a good understanding of trigonometry, and inverse trig is part of that. So we're going to get right into what are the derivatives of inverse sine, inverse cosine, and inverse tangent, and we'll try to see an example of each of them. Okay, let's go ahead and see what we can do. So let's start with inverse trig functions and their derivatives. Let's start with the question of what is the derivative of inverse sine of x. Of course, in this class, we've already talked about derivatives of things like sine and cosine and tangent, the ordinary trig functions, right? And now we need to talk about their inverses. Oh, by the way, I'll kind of make an analogy here. You know how earlier in this course we had a lesson about derivatives of exponential functions? Now, you might say, what does that have to do with trig? We had a lesson on derivatives of exponential functions. And then recently, we just had a lesson about derivatives of logarithmic functions. Well, exponentials and logarithms are inverses of each other. And of course, sine and inverse sine are inverses of each other. So it seems like maybe we can derive a rule for this in a similar way to what we did for log functions. That's just kind of an analogy, but yeah, it is going to work kind of that way. If you compare these notes with the previous lesson on log functions, there's going to be some similarities. I'm going to start by saying let y equals sine inverse of x. That's the function that we're interested in, so we could just call it y. And now we would like to find dy dx. Then, by the definition of inverse sine, we know that x is equal to sine y. Right? These two things are equivalent to each other. Y equals inverse sine of x is the same as x being equal to sine of y. That's what it means to be an inverse. The x's and y's trade places. And now, just like we did in the logarithmic lesson, we're going to use implicit differentiation. We're hoping to establish a rule or a formula for what dy dx is. And when we do implicit differentiation, we usually get a dy dx that pops out. So I think this is going to work. D dx of each side, right? D dx of x equals d dx of sine y. So the left-hand side is actually just 1. D dx of sine y, you should know by now that this is going to give us cosine y times dy dx. But I'm happy to see that because we're trying to find dy dx. So rearrange things, divide both sides by cosine y, and we get this. Do you see the similarity to the logarithmic lesson? We want to find the derivative of something that we know is an inverse function. So we use the definition of inverse to rewrite it in this way, and then we apply implicit differentiation. We finished the implicit differentiation part. I'm not putting a box around this yet, though. So I don't want to say this is the formula because look at the question. The question was just in terms of x. So I would really prefer, if possible, to find an answer that's just in terms of x, because y is something that we introduced ourselves to help us along with the problem. but the problem didn't have y in it to begin with. All right, so let's say, but we want a formula in terms of preferably just x. Because if you think about it, like when I've asked you in this class, what's the derivative, what's d dx of e to the x? What's d dx of cosine of x, tangent of x, x to the 100? We always try to get answers that are just in terms of x. So yeah, we want a formula just in terms of x. Now, what can we do though? Do we have anything we could work with? I see one thing. I see this. Y is inverse sine of x. So maybe we could take this formula and instead of writing y, we could put this here. I'm going to say this is one idea. This is actually not the best that we can do, but let's at least acknowledge that this would get it in terms of just x. See what I did? I replaced y with inverse sine of x because y is inverse sine of x. All right, I'm going to say, but there is a nicer formula we can find. So I'm not putting a box around that. That's not going to be the rule that we stick with. Because that's kind of weird, right? It's kind of weird to say 1 over cosine of inverse sine. Now, there's something that we can use, and this is something that, we were not able to use in the logarithmic lesson. We're going to be able to use trig identities. We can use what we know about trig functions, and trig identities let us rewrite trig functions in other terms, right? In other ways. Maybe an analogy that I could make here is that in the lesson on logarithmic derivatives, we used rules that we know for logarithms, shortcuts and properties and laws of logarithms. So now, if we're talking about trig, let's use trig identities. So we're going to use everyone's favorite trig identity. It's my favorite trig identity, at least. Sine squared plus cosine squared equals 1. Now that's true whether the variable is called y, or whether the variable is called x, or whether the variable is called theta. Whatever you call it, sine squared of something plus cosine squared of the same thing gives you 1. Now, how is that going to help us? We're going to be trying to work from here. I'm going to put like a tentative box around this. This is the thing that I would like to find a better form of. How about this? Let's try to solve for cosine. I mean, I want to solve for cosine of y. I just solved for cosine squared of y. So let's take the square root of both sides. Cosine y is equal to the square root of 1 minus sine squared y. Something just happened here. We took a square root of both sides, and usually you would expect to have a plus or a minus sign show up. But I didn't write the plus or minus sign. I just wrote it as positive. Do you know why I did that? Well, it has to do with the domain and range that we're working with when we talk about inverse sine of x. In our final rule, we're going to actually specify what the domain is for x. So anyway, for the x values that we're interested in, cosine is always going to be positive. Okay? And I didn't really go into much detail about, the domain and range of inverse sine of x, but that's where this is coming from. Things are positive in this. Now, does this help us? Like, if I took this formula, but instead of writing cosine y, if I wrote this, Is that really any better? That actually looks more complicated. Well, there is something we know from our page that will help us. Do you see it? It's this thing here. See what I'm pointing at? X equals sine of y. So x equals sine of y, or in other words, sine of y equals x. So that means that cosine of y could be thought of as 1 minus x squared. This was from above. Now this is nice. This is nice because it means that we could take the formula that I put kind of a tentative box around, but instead of writing cosine y, I can write this. Square root of 1 minus x squared. And we're going to get, finally, this rule. The derivative of inverse sine of x, and this is going to be an answer just in terms of x. 1 over the square root of 1 minus x squared. And I'm going to say off to the side where negative 1 is less than x is less than 1. So this is not something that we use for all real numbers x. Because if you remember back to when you first learned about inverse trig, you can't put in, like it doesn't work for all real numbers x, right? Like what's inverse sine of 2? It's undefined. But we can do anything in here. All right, so this is a formula that we can use, and we don't have to derive it every time we want to use it. We can just use this and solve some problems. So let's do a problem. Of course, just like with other rules that we've learned, you're probably not going to get asked just for what's the derivative of inverse sine. It's probably going to be something where you need to combine it with other things we know. So this problem, which I will do, is we're given inverse sine of e to the x plus x, and we would like to find y prime. All right, so I'll do this one. Of course, we're going to use this new rule that we just derived, and we'll figure out what else we need. Inverse sine of, so it's not just inverse sine of x, it's inverse sine of this stuff. So it's a chain rule problem. It's a chain rule problem where the outer function is inverse sine and the inner function is the stuff that's in parentheses. Of course, by now, you know, we don't have to write out all of these chain rule steps. We could do some of this in our head. Maybe I'll talk about that afterwards. But this is e to the x plus 1, and this is 1 over square root of 1 minus u squared. What does the chain rule formula tell us? F prime of g of x times g prime of x. All right. Are we ready to put this all together? F prime is 1 over the square root of 1 minus something squared, but it needs to be this instead of u, e to the x plus x. So let's write that part. 1 over square root of 1 minus something squared. It's this stuff that gets squared. All of that times g prime. And I think we should put parentheses around g prime to make sure that the e to the x and the plus 1 stay together as one object. We're gonna write this like one more step, I think. Just one more step to maybe make this look nicer. Is I'm gonna take the times this stuff and I'm gonna just put it up top. I'm gonna say e to the x plus 1 over this. I think this is a good answer. And put a box around that. All right, so I said something in the middle of the problem about how we might be able to do this without showing so many steps. Do you think we can do some chain rule stuff in our head by now? How about, I know that when we do the chain rule, it's always the derivative rule for the outer function of the inner function times derivative of the inside. So when I see inverse sine, I should think to myself, hey, what's the derivative rule for inverse sine? Oh, wait, we moved the paper away. Here it is. What's the derivative rule for inverse sine? It's right here. Okay, so it's going to, I know fundamentally my answer is going to look something like this form. It's going to be 1 over square root of 1 minus something squared. But the something is going to be the inner function. That is what we wound up with. And then it needs to be times the derivative of the inside. That's this piece here. So I really think that you could do this without writing f of u, g of x, f prime, g prime, as long as you remember chain rule is derivative of the outside of the inside times derivative of the inside. Okay. But there's no harm in writing out all these steps. All right, so that is inverse sine. It makes sense that now we would talk about inverse cosine and see if maybe we get a similar rule. Why do I think it's going to be similar? Well, because the derivatives of sine and cosine were similar to each other. So maybe the inverse versions are going to be similar also. And, you know, sine and cosine go hand in hand with each other. So we'll see what we get. All right, we'll pose this as a question again. How about this? Think about what we did in the previous step, and I'm going to encourage you to try it. See if you can figure out the rule. Maybe pause the video and compare with what we did for inverse sine, and then check back with me. All right, so what we wind up with is we let y equal inverse cosine of x. We say, well, by the definition of inverse cosine, that means that x is cosine of y. We say we want to use implicit differentiation on this. Right? It's a good place to start. D dx of both sides is going to give us 1 equals negative sine y times dy dx. The negative is because derivative of cosine is negative sine. And then we get dy dx equals negative 1 over sine y. And this is kind of that tentative step, right? It's like kind of a formula, but it's not the finished formula. Because we want an answer in terms of x. So we need to see, what can we do? What can we do? Maybe we can use the same trig identity that we used before. What do you think about that? Sine squared y plus cosine squared y equals 1. When we did inverse sine earlier, I guess the formula that we had a cosine in it. So we took this trig identity and we solved for cosine. This time, the formula has sine. So I'm going to take this and solve for sine. Solve for sine of y. So sine squared of y is 1 minus cosine squared y. Sine of y is going to be the square root of 1 minus cosine squared y. And we know that cosine of y equals x. Do you see where I got that from? From above? I'll point it out. It's from this line here. X is cosine y. So we're going to be able to put that in and say that this is 1 minus x squared. And the result, the rule that we just found, is that the derivative of inverse cosine of x is, well, let's be careful here. We're taking this formula, but we're going to rewrite it in terms of x. Don't forget that this has a minus out front. The minus has to be in our answer here, right? So minus 1 over square root 1 minus x squared. And I'll say where negative 1 is less than x is less than 1. Okay, cool. What do you think? What do you think? Did we get a similar rule to what we had for inverse sine? Let's see if I can fit these both on the screen. The one we did earlier and the one we just did now. Hey, look at that. Look at how similar they are. Of course, you're going to have to remember which is which. But I think the fact that they're so similar helps. If you can remember one, it helps you remember the other. Just remember which one needs the minus out front. Let's get another sheet of paper. We're going to move these rules away, but I think we've got them in our notes by now. So earlier we derived a rule for inverse sine, and then there was one example problem. We just derived a rule for inverse cosine, so let's do one example problem. All right, so given y equals, I'm going to ask you to try this one. Y equals inverse sine x times inverse cosine x. And it's going to say find y prime and simplify. So I'd like you to pause the video and give this a shot. All right, so this looks like a product. It's something times something, and we just, discussed a rule for the first piece and a rule for the second piece, but we also need to acknowledge that it's product rule. So, all right, that's okay. Let's get started. Y prime equals the first function times derivative of the second. Sometimes I add extra parentheses that might not technically be needed, but my thought on that is it's better to have too many parentheses rather than not enough, and we can always make sure that our answer has just the right amount of parentheses. So I'm grouping together, each of the 4 pieces of the product rule in parentheses. All right, so we differentiated. I mean, that is the derivative. That's y prime. And now the only thing remaining is to see if we could simplify. I think we could do some work with this, right? We could see what happens. Like, what if I multiply this times this? We get negative inverse sine x up top over 1 minus x squared. That's my first piece. Second piece, let's do that with this also. Let's multiply and get inverse cosine of x up top and this on the bottom. What I was hoping you would notice is that when you do this problem, you sort of naturally wind up with a common denominator. And if you have a fraction plus a fraction and the denominator is the same, you can combine it into one fraction, right? One fraction where this is the denominator. And there's a couple of ways we could do this. We could write up top for the numerator, we could say negative inverse sine x plus inverse cosine x. For some reason, I decided to put the cosine first. Inverse cosine x minus inverse sine. You know, of course, you could also say minus inverse sine plus inverse cosine. But I think that combining, because of the common denominator, I think I'd like to see the answer in one of these two forms. So we've talked about the derivative rule for inverse sine and the derivative rule for inverse cosine, and then we've had one example problem for each. So what do you think we have left? There are 6 trig functions, right? Well, I'll tell you, we're only going to look at the derivatives of the inverses for 3 of them, sine, cosine, and tangent. So we need to talk about inverse tangent. So let's do that. Oh, this one might have a different kind of rule, right? Because sine and cosine always seem like they go together. They've got similar rules. Tangent might be something different. What is... And I'm not going to make you derive this one. I'll kind of talk us through it. What is the derivative of inverse tangent of x? But I think we can use a similar strategy to what we did earlier. I think you could do this. I'll just kind of talk us through it, though. Let y equal inverse tangent of x. Then x equals tangent of y, and we want to use implicit differentiation. D dx of the left and d dx of the right. Ooh, what is d dx of tangent y? I mean, I know that the left-hand side is just going to be 1. D dx of tangent y, do you remember what the derivative rule is for tangent? If you don't, you could always figure it out again by making, you know, just strictly speaking of like derivative of tangent, you could always find it the way we originally found it. We rewrote tangent as sine over cosine, and we used the quotient rule. Anyway, the derivative of tangent x is secant squared x. So this is going to be secant squared y times dy dx. And from that, dy dx is 1 over secant squared y. Of course, that's not the finished formula because it's in terms of y. We'd like it to be in terms of x. All right. But we want in terms of x. You know, for sine and cosine, we used the same trig identity for both of them. Is there some way that we could use this trig identity? Do you think we could use this? Or do you think we need a different identity to like somehow solve for secant of y or secant squared of y in terms of something else? I'll show you a cool trick. I mean, you've probably seen this before at some point in your math classes. What if you take this and divide both sides by cosine squared. So the usual sine squared plus cosine squared equals 1, but I'm going to divide everything by cosine squared y. So sine squared y over cosine squared y plus cosine squared y over cosine squared y. This is just a way to get new trig identities. Like start from a trig identity and do something to it. And you're going to wind up getting a new trig identity. What does this wind up equaling? Sine squared over cosine squared is tangent squared y. Cosine squared over itself is 1. 1 over cosine squared is also known as secant squared. That's pretty cool, right? Here, let's section this off as like that was a bit of trig identity work. Now, the bottom line that I wrote here, tangent squared y plus 1 equals secant squared y, you've probably seen this at some point, like in a pre-calculus or a trig class. You know, you've probably seen this line, and it was probably taught to you as a trig identity. But this is where it comes from. It comes from, that's why I said this is my favorite trig identity. Sine squared plus cosine squared equals 1, because you can do so much with it, and you can quickly get new identities like this one. Well, this tells me that secant squared y, you know, this can be rewritten as 1 plus tangent squared y. I said that we wanted to get the answer in terms of x, and you could look at this and say, you know, well, wait a second, that's not in terms of x. But look at this. Look at this. X is tangent of y. So let's put that in. So I'll say, and we know that tangent of y equals x from above. So what is this going to look like if I replace tangent y with x? The result that we get is the derivative of inverse tangent of x equals 1 over 1 plus x squared. Pretty cool rule. It's pretty good. That one doesn't have any square roots in the answer. By the way, there's 2 things that I want to say about this rule. Let me just give you a chance to catch up in case you're still writing any of that. All right, 2 things I want to say. First thing is that this formula actually works for any real number x. There's not like that restriction of x having to be between -1 and 1. This actually works for any real number. So why does this work for any real number? It's because when you originally learned in a pre-calculus class about inverse tangent, you should have learned that the domain of inverse tangent is all real numbers. The second thing that I want to say about this is that this rule, I mean, you might think sine and cosine are the most important of the trig functions. I wouldn't blame you if you think that. You know, sine and cosine come up quite a lot. I want to tell you, though, that this rule is actually pretty important for Calculus 2. So for those of you who plan to take Calculus 2, maybe put a little star next to this in your notes or highlight it or something. This is actually going to be seen more often than you might think. Let's do an example problem. We did example problems for the other 2, so we should do one for this. Example. given y equals, some brackets around this, inverse tangent of x to the fifth. I think I'd like you to try this one. Find y prime and simplify. So you can pause and give this one a shot. All right, it's inverse tangent of x, but it's being raised to the fifth. So I feel like the brackets and the raising to the fifth, that seems to suggest to me that the chain rule is happening here, because it's a function on the inside of the brackets, and raising to the fifth would be the outer function. So let's set it up this way. Of course, we just learned the rule for the derivative of inverse tangent, so let's write that 1 over 1 plus x squared. And we know this derivative over here is 5u to the fourth. Use the chain rule formula. Okay, we can put all these pieces together, right? You get 5. You need some kind of parentheses or brackets here. Inverse tangent of x to the fourth times derivative of the inner function, so times this. Is there anything we can do to simplify this? It's not really that bad the way it is, but I think it would be nice to take this stuff, instead of having it be multiplied times a fraction, let's just take this stuff and move it up top, make it the numerator. So I wrote this as 5 parentheses inverse tangent of x to the fourth. All of that is over 1 plus x squared. And that's a good answer. I guess I should tell you off to the side. So this is the answer, but, you know, just be careful. Inverse tangent of x to the fourth is not this. I'll put that in parentheses. So sometimes, you know, sometimes you could try to simplify too far and like make mistakes in simplifying. The way that I put a box around it, I would just leave it like that. We can't really simplify any further. This note off to the side, by the way, you know, the reason I'm pointing this out is because it's kind of unfortunate, the notation that we use for inverse functions. Isn't it kind of unfortunate that we use a -1 that looks like an exponent? It can be confusing, right? Because you know that all day today in this lesson, I've been doing things like this: sine squared of y, cosine squared of y, and we always write an exponent like sine raised to an exponent, cosine raised to an exponent. But you have to remember that when there's a -1, technically that's not an exponent. If it's on a trig function, it means the inverse function of tangent. I wish we had a better notation. I guess you could say that, in a way, there is another notation. So we'll make this our one more thing for today. Inverse sine, inverse cosine, and inverse tangent. You may have heard this at some point, but they're also known as arc sine, arc cosine, and arc tangent. So, you know what? Maybe those names are pretty nice. Maybe we should use those names, because the -1s, it's easy to confuse them for exponents. But I guess the reason I use the -1 notation is because that's the most popular notation, and I like to use the same things that you might see in a textbook. So, yep, that's going to be it for this lesson. So we'll wrap up here. So what did we do in this lesson? We learned derivative rules for inverse sine, inverse cosine, and inverse tangent, and we did one example of each, type of problem. Some of them use the chain rule, some of them use the product rule. I don't know if we use the quotient rule today, but you know, we've got a lot of derivative rules now, and they could be combined. You could get a problem that needs to use one of these with a log function or implicit differentiation or quotient rule or chain rule twice, right? So you understand that there are a lot of different types of derivative problems that we can solve now. And at this point in the course, we want to practice lots and lots of derivative problems to get good at them. But I think by now you're already getting pretty good at derivatives. So the good news is that I feel like at this point in the course, we're kind of done with our big batch of derivative rules. And where we're going to go from here in upcoming lessons is we're going to sort of shift to looking at applications of the derivative. What can the derivative do for us? What can it be used for? And some of that is going to be like word problems, but some of it is going to be other things. So I know we've had a lot of formulas in this class, but we'll still have some more formulas, I guess. But I feel like we are, in a way, we're kind of moving on from the portion of the course where we were just piling on formula after formula. So, all right, that's it for today. And thank you for watching. So take care, and I'll see you soon.